Welcome! Today we want to build a fully automated, small-scale, do-it-yourself, continuous fractionating column. But how are we gonna do that? Well, here's the plan. First of all, we need to think about what feedstock to use. And we need to characterize this feedstock so that we get the needed values or the values needed for dimensioning of the column. Well, second, we look at the column itself, in which the separation of the components with the higher boiling points and the lower boiling points take place. Third, we look at the evaporator, in which the vapors are generated which rise through the column. And fourth, we look at the condenser, in which the vapors are condensed. And at the recooler, which provides the coolant to cool the vapors in the condenser. Then we have the main components of this apparatus. And what we need next is the electronics to run it and the software to provide all the measurement values and the controls on a nice looking graphical user interface. In order to reach a steady state operation, we also need a control scheme which is able to provide that. And at last, I'm going to show you the operation and the functionality of this fractionating column. Well, these are a lot of points. I hope you have a little bit of time. Let's go. Let's start with the feedstock. Well, there are different options what you can distillate, and fractionating distillation takes a big role in industry for many different mixtures, but doing it yourself, you're a little bit more limited and you want to do it safely. So first of all, I thought, well, the classical alcohol-water mixture would be an option. But alcohol has a lower boiling point than water, and therefore you have flammable, also explosive vapors inside the column head, which isn't that good or safe anyway. A better option would be perhaps acetic acid, because it has a higher boiling point than water, and so the risk of fire and explosions is reduced. But acetic acid is corrosive, and therefore we probably would get problems with the chemical resistance of our apparatus itself, especially at the high temperatures you need to boil it. And the last option is propylene glycol or 1,2-propane diol and water, which is basically really easy to separate because of the large boiling point difference, but is also pretty safe to handle. And therefore, I have chosen the propylene glycol water mixture to demonstrate the function of this fractionating column. Propylene glycol is used in electric cigarettes as a main component to create this vapor, and in smoke generators, and it is also used in cosmetics and has a rather high boiling point and therefore a low probability of building flammable vapors. Therefore, it is relatively safe, and that's the main reason why I choose this as the example mixture. Well, now we have chosen the mixture we want to separate. Next, we need to get some characteristics of this mixture in order to dimension our separation column. And we do that by performing a simple standard distillation. almost standard. As you can see here, we have a round bottom flask with the mixture in the bottom. We have a temperature sensor with which we measure the temperature right at the phase interface to get the correct temperature to our vapor liquid equilibrium. We have the condenser, and what's now different from a standard operation, standard distillation, is that we reflux the distillate. We pump it back inside the round bottom flask, and we do it as long as some stable condition is reached. And if the stable condition is reached, we sample the distillate, which has the same composition as the vapors, and we sample the bottoms. And now we can we have the equilibrium composition of vapors and bottoms at a certain temperature. We analyze this using a refractometer for the product analysis, and if we perform this with different compositions at the start of this distillation procedure, we can get different points in this diagram. In this diagram you can see the equilibrium composition and the equilibrium mole fraction of water in the vapor phase and mole fraction of water in the liquid phase. The red points show you literature data, and the blue ones show you the data I measured, and the black line here is the fit of the data we're going to use for the dimensioning of the column. So now we have this data and can start dimensioning the column, the separation column. And this, it's going to be a little bit theoretical, but I promise it's only this slide which is slightly more complicated than the other ones. And it's only a rough overlook over how to do it in principle. Well, you have this equilibrium curve inside a diagram we measured, but in our real fractionating column we don't have the equilibrium concentrations in every stage because there is not a time to reach the thermodynamic equilibrium. And we also have product removal and feed input into the column. So therefore we have an operation line inside this diagram where you can see for different heights inside a fractionating column which composition the liquid and the gas phase do have. This operation line can be derived by making a material balance. Yeah, for example, in this picture, we only look at the bottom part of the fractionating column and make a balance what moles are flowing inside and what moles are flowing out of the column. And from this balance, the operation line can be determined. And now you can see there is a difference between the equilibrium composition of liquid and gas phase and of the operation composition of the liquid and gas phase. And the bigger the distance between both of those compositions, the bigger is the thermodynamic drive for mass transfer, or the bigger is the drive for mass transfer and for the separation to happen. And this basically determines how large or how tall the column needs to be to reach the desired composition at the bottom and at the top of the column. If we have a closer look at a mass transfer inside a column, we can make a balance for a very, very small piece with the height dH. And in this small piece, you have the gas phase and you have the liquid phase. And in those, you have concentration gradients to the phase, to the border between the phases, the interface between the phases. Right at the interface, you have the in rough estimate, you have the equilibrium fractions of water inside a liquid and inside a gas. And then going into the bulk of the phase, you have the operation composition. And now looking at this small fraction, you have molar flows leaving and entering these small sections. We make a balance, and you can write down the balance and see you can integrate this small fractions over the complete column in order to get a complete height. And if you integrate that from the desired molar fraction of water inside the bottom product to the desired molar fraction of water inside the top product, you basically get the necessary height of this fractionating column. So as you see, it's a quite complicated calculation, and it's even more complicated if you look in it in detail, because here you have some things like mass transfer coefficients, for which you can find difficult correlations in literature, for example in this paper from Onda. Therefore, I'm not going into more detail at this point. If you want to perform such a calculation by yourself, you can look at the book of Schlünder and at a publication of Onda to get the desired or the needed equations to do so. But what we learn from this little explanations about mass transfer in fractionating columns is simply that the height of the column needs to be enough for the mass transfer to result in the desired molar fractions at the top and the bottom of the column. That's the way how we determine the needed height of this apparatus. Now we have the height, and next we look at a diameter. And the diameter depends on the hydrodynamics inside this column. In this diagram, you can see on one axis the superficial gas velocity of the vapors rising inside of this column, and the superficial liquid velocity of the liquids flowing down from the top to the bottom of the column. And in this diagram, we can see there are different regions. We have a blue line at which, and over this, above this blue line, flooding occurs, which means if we have higher superficial liquid velocities, meaning we have a bigger liquid flow flowing through this column, and we also have a high superficial gas velocity, then the liquid flowing down the column can at one point not efficiently flow down completely, because the way is blocked by the gas, and the gas has enough friction to hold the liquid more or less in place. So the column itself fills itself with liquid, and it's flooded. And then the pressure loss increases dramatically, and it's difficult for the vapors to reach the top of the column. This is not an operating point or situation we want to achieve with our column. So we want to stay below this flooding line when we choose the diameter of the column. Then we have another limitation, which is the breakup of the liquid film. If the superficial liquid velocity becomes too low, we don't have a closed large liquid film inside the fractionating column, which we basically need to have the large surface area needed for the mass transfer and for the separation to happen. So we need a minimal superficial liquid velocity to have a sufficient liquid film for mass transfer to happen. And both of these, the superficial gas velocity and the superficial liquid velocity, are affected by the diameter of the column. For example, we have a fixed volume flow rate of feed inside a column and of liquid and of gas, And now the velocities, if the volume flow rate is fixed, the velocity only depends on the diameter of the column and of course of the porosity of the packing material, because we in our case are building a packed fractionating column. So if you have a bigger diameter of the column, if the diameter is too big, and we have a limited volume flow rate of liquid, then the superficial liquid velocity becomes too low and we get this breakup of liquid film we don't want to have because of our mass transfer. If the diameter of the column becomes too small, then the superficial gas velocity becomes too high and we run into flooding the column. So we want to operate the column in this operating region where we don't have this breakup of liquid film and don't have the flooding. And if you want to calculate those lines or have some rules of thumb for them, you can look at the publications linked below of this diagram. Well, I've chosen a quite small diameter of the column, a very small diameter of the column of only 10 millimeters. Why I did so? Because the column gets more expensive the larger the diameter is, and it's harder to manufacture and to work with tubes with bigger diameters if you do it yourself, and it's more expensive because you need bigger fittings and those are expensive. So I tried to run this column with an inner diameter of only 10 millimeters, and therefore some of the packing materials I initially planned to use didn't work. I initially wanted to test structured packings which are 3D printed with PEEK material and which I designed myself, but they didn't work because the porosity was then too low, and so the velocities were too high and flooding occurred. I also initially designed the complete column using glass spheres as packing material, and these glass spheres would be held in place using copper wool inside the tubing, but unfortunately I made a mistake in the calculation of this of the column diameter, and so working the column with the glass spheres didn't work, at least at the volume flow rates of feed I want to achieve, so that I don't have to wait forever for the operation to finish. So in the end, I only used the copper wool as packing material to increase the surface area for mass transfer a little bit, but this copper wool also has a high porosity and therefore reduces the velocities, the actual velocities in the column, so that no flooding occurs and vapors also reach the condenser and we had a top product. So that is the way how to dimension the separation column, the height and the diameter of the column. And next, we need to generate the vapors which rise through the column. And we do that using a natural circulation evaporator. The evaporator is at the bottom of this separating column, meaning the feed is flowing into the column at this point. It is liquid, the feed in this case, therefore it is flowing down. So some of it evaporates by the heat transferred from the rising vapors, and the liquid then flows further down inside the bottom and reach the evaporator section. The heating element finally is here on the right side. It is heated up, and then you have some kind of pumping effect from the natural circulation from the gas bubbles which build up due to the boiling. They rise the liquid and the vapors up, into this cross section where they are separated more or less, because we only have a very small pipe diameter, and the liquid can flow down again and in the evaporator again, and the vapors they rise inside this separation column, where they are further separated into the water vapor and into the propylene glycol rich liquid fractions. Let's have a closer look at the evaporator heating element. And this heating element is shown here. It basically is a piece of copper pipe, and around this copper pipe there is a nickel chrome wire which is wound around it, and now we run current through it, therefore heating it, and that's all. That's basically our evaporator. In order not to short the nickel chrome wire by the copper tubing, it is isolated using Kapton tape. One problem of this method is that there are local hotspots in the heating wire. You can see it on this picture, because the heating wire doesn't contact the tubing ideally at each point. Especially if it is heated, then it expands a little bit and you have even less contact. So I have a question: if you have an idea how to wind this better, so that you have fewer hot spots in this evaporator, you can put this idea in the video comments. That would be interesting at this point. Nevertheless, even though we have these hotspots, I were able to run this column and this evaporator successfully without damaging the heating wire. The only points where they burn through occasionally was the connection down there, because my soldering skills aren't that good, and therefore it heated through at this point, and I have to shorten that heating wire a little bit to have a good connection, or to make a good connection again. But these hotspots at the top, they were quite fine. You also have some piece of Teflon tubing at the bottom, which is a compensator element, and this is at this point to compensate for the thermal expansion of the evaporator section, so that the thermal expansion doesn't result in leakages inside of these fittings because of the forces they generate. And there is also a thermocouple right at the top of this heating element, which contacts not the heating element wire, but the tube wall, because it's the tube wall temperature which is mainly interesting for boiling and for evaporation of the liquid. So how to size this evaporator? Well, first of all, the heat we need to introduce to generate this vapor can be calculated by the molar flow rate of the gases multiplied by the heat of evaporation of this mixture. And with this, we can calculate the minimum amount of heat flow necessary for the evaporation. Of course, you have losses and something like that. Therefore, in reality, you need a slightly higher heat flow, and therefore the design heat flow or heating power is higher. I choose the design heating power of 250 watts, and with this design heating power, you now can calculate the necessary length of the nickel chrome wire using the specific resistance of the nickel chrome wire. Basically, you calculate the current running through the wire by dividing the operating voltage by the resistance of the wire, and then multiply it with the voltage, and voltage times the current is the power. at this point. So in this way you can calculate the needed length of the heating wire, but it is not enough to just have a long enough heating wire. The heat also needs to be transferred from the tubing to the liquid inside of this apparatus. And therefore the tube needs to be long enough and the surface area between tube and liquid needs to be large enough. Therefore you also have to make a heat transfer calculation using this classical formula for the heat transfer between a solid and a liquid. And in this you have the temperature difference between the tube and the boiling liquid. You have the surface area and you have the heat transfer coefficient, for which I don't use any fancy correlations for boiling liquids inside of vertical tubes or something. I just used an estimated value I get from this publication. And with that, I estimated the necessary tube length necessary for the heating of the liquid in the evaporator. So after all, the tube needs to be long enough for the needed heat transfer to happen, and the heating wire needs to be short enough for sufficient current flow, which generates enough heat, and long enough to distribute this heat over the complete length of our pipe, basically. Now we talked about the element which generates the vapor and introduces heat into the apparatus. Next we look at the element which removes the heat and condenses the vapors in the head of the column. And this is the condenser at the top. You can see it at this point here. And the condenser basically is a double tube heat exchanger. It exchanges the heat between the vapors or the condensate and the cooling liquid flowing outside. In the inside you have the copper tubing, which is the same tubing as in the fractionating column with an inner diameter of 10 millimeters. And outside you have some slit where the liquid, the coolant, flows, which is formed between the copper tube in the inside and this garden hose piping or tubing on the outside. And I use this flexible garden hose tubing on the outside also to compensate thermal expansion, because I used fittings here, screw fittings, to screw it all together. If you don't regard this thermal expansion, it could be that they start leaking. Therefore, thermal compensation is necessary. So this condenser needs a defined length in order for the condensation to happen completely. And you can calculate the length in a similar way than we calculated the length of the evaporator tube. First, we have to calculate the heat we need to remove to condensate the vapor, which is basically the molar flow rate of the vapor multiplied with the enthalpy change of condensation or the enthalpy change of evaporation, which simply have different, the one is minus, the other is plus, basically. And this also is the minimum value. The design value should be a little bit larger. And here you again have this heat transfer equation in which we have this heat transfer coefficient, which now I estimated using this book mentioned in this citation. In this way, you can dimension the length of the condenser tubing, and then we need a sufficient supply of cooling liquid, which can absorb all of this heat. And this cooling liquid is supplied by the recooler unit, which is shown here. The recooler unit is built from basic PC or computer cooling components, meaning we have a 360 millimeter radiator on top with 3 fans which push the air through the radiator, and a cooling pump with a small container with the cooling liquid, and the cooling pump runs the cooling liquid through the radiator and then through the condenser and back again in this container. And from the outside, the heat is then absorbed by the air running through the recooler. So the cooling liquid transfers its heat to the surrounding air. That's all. And in order to dimension this type of device, I just used a review article for different computer cooling radiators available at this website, and there they have a list of many different radiators they tested, and 360 millimeter radiators, they dissipated between 235 and 319 watts of heat if fans with a speed of 1300 rpm were used and the flow rate of the coolant of 1 gallon per minute at a temperature difference of 10 kelvins between the coolant and the ambient air. So using such a recooler should be enough for our application, because we only put in around 250 watts in the bottom of the column, and such radiator is able to remove between 235 and 319 watts. I used slightly faster fans with 1800 rpms revolutions per minute and slightly higher flow rate. Also we could also higher temperature difference would work in our setup. So this recooler unit should be more than enough to withdraw those 250 watts of heat from our fractional distillation column apparatus. So basically the condenser needs to be long enough to transfer the heat of condensation to the cooling liquid, and the recooler needs to be able to remove this heat from the cooling liquid and dissipate it in the ambient air. So now we have all the components together from the main apparatus, and next let's look at the electronics to move the parts and to heat it and cool it and to let it all come alive. So this is the first module of the electronics. This is the heater and temperature measurement module. Here we have an Arduino microcontroller which controls all of it, and this Arduino is connected with 3 thermocouple modules which communicate with the Arduino using the serial peripheral interface. So they have some common wires and are only differentiated by this chip select wire, so we can select which thermocouple we want to read at a certain moment. One important detail at this point is that I added additionally capacitors at the input of the thermocouple wires, which are not included in this thermocouple modules I purchased, because the pumps and the heating element, they introduce a lot of electromagnetic noise in the environment and therefore badly influence the temperature measurement. And these capacitors are able to filter out this noise and result in useful temperature measurements. Then we have the heating element. This is our nickel chrome wire, which is around the evaporator tube. It has a resistance of 5.6 ohms and is supplied with a 30-volt power supply and controlled using this MOSFET by pulse width modulation. Next we look at the pumps. The pump for the feed inside into the column, and the pumps for the reflux of the condensate into the column, which runs back to increase the separation. And this is controlled by a separate microcontroller, by a separate Arduino, and the pumps are basically driven using the L293D motor driver integrated circuits. So it's quite easy. Only the wiring is, there is a lot of wiring, but it's easy to drive those motors using this motor driver ICs. There is one detail in this circuit I want to mention. These pumps I used are designed to work at higher duty cycles and at higher flow rates than I want them to work, and therefore I had problems with the pulse width modulation at low duty cycles because there the pumps or the motors doesn't start, and I couldn't achieve the low flow rates I wanted to achieve at first. Therefore, I solved this problem using higher capacitance at a power supply, which is able to provide the high startup currents at the beginning of those low duty cycles so that the motors start up at least. And I also increased the overall period duration so that the motors run at least a bit in this period. And with those two tricks, I was able to run these motors even at the low flow rates I want to achieve. So that's basically about the pumping of the main fractionating column. Next, we look at the cooling circuit. You can see it here. We have another Arduino Nano microcontroller, another L293D motor driver modules, and with them we run the fans, which push the air through the 360mm radiator, and we run the coolant pump, which pumps the coolant through the radiator and through the condenser. Here is interesting to note that the fans, they have an additional pin which can be used to get their speed, but you only can do that if you don't use pulse width modulation. Therefore, I run them at full speed. I mean, I wanted maximal cooling capacity anyway, and at full speed, we are able to measure the revolutions per minute using this additional pin and display it in our graphical user interface. So the last circuit diagram I want to show you is the pressure measurement module. Here we have basically 3 different pressure measurement modules which measure the pressure right downstream of the 3 pumps inside our apparatus. And that is for monitoring proper operation of the pumps. Yeah, if they generate the pressure we want to have in order to pump liquid through our apparatus. And that's all at this point. So now we have all the electronics on the microcontroller side. Let's connect it to the computer so we then can control everything from the computer. And you can see the connection in this chart. We have the computer or the laptop on which the main program runs, which is a Python script called column.py. And in this Python script, we use a custom Tkinter for the graphical user interface and matplotlib to plot the diagrams and so on. And this sends serial comments to the Arduinos using an USB hub. And the Arduinos send serial data back to the computer, which contains the measurement values. The message looks like this. If the computer sends an instruction to the Arduino, the Arduino gets the single characters, because it receives the single characters so fast and clears the buffer so fast. The Arduino only sees single characters, and therefore we need a start and the end marker, so the Arduino knows where the message starts and where it ends. And inside these markers we now have the main message, which is the Arduino's name. We're gonna address them by the name to control if the correct Arduino gets the correct message, which is meant for him. Then the second point of information is the actor name. For example, we push the button for the fan number 1 or for the feed pump inside of our graphical user interface. And then here the actor name is feed pump, for example. So the Arduino knows, oh, well, we have to run the feed pump with another value, and the value is also given in the message. And this is basically the duty cycle of the feed pump. Or if we have calibrated it, which I have, you can send the Arduino the desired flow rate, and the Arduino then calculates the necessary duty cycle for the pulse width modulation of the pumps. So these are the instructions the computer sends to the Arduinos, and the other way around we have the measurement values, which are sent to the from the Arduino to the computer. You have the variable names and their values, and they are sent to the computer and are displayed on the graphical user interface. So this is the communication between the Arduinos and the computer. Now let's have a look at the program running on the computer. And this is, as I mentioned, a Python script, and it contains 4 different type of loops. First, we have the read serial loops. There are 3 of them, and their function is it to read the serial messages the Arduino sent to the computer, to process the serial messages, and to save the variables. Yeah, for example, the Arduino pressure module sends the pressure values to the computer, and it saves these pressure values in variables which are displayed on the graphical user interface and which are saved in the data using the second loop, which is the save data loop. This loop waits for all the variables to be actual and then saves the variables in the comma separated value file. This comma separated value file is read by the animate function. This reads this file and plots the values in the graphical user interface using the matplotlib library. And last but most importantly, we have the main loop, which is the custom Tkinter main loop to run the graphical user interface. This main loop checks the user interface for user interaction. For example, have I pressed a button to start a pump or something like that? And if that's the case, then it sends the instructions to the Arduinos, and it displays all the values and all the artwork on the graphical user interface. So these are basically the 4 main types of loop you're gonna find in the Python program. Then after the Python program, let's have a look at the Arduino programs, which are all structured in a similar way. The Arduino programs all have this receive instructions function, which receives the individual characters of the message, which is sent from the computer to the Arduino microcontrollers. And in this receive instruction function, the message is assembled out of these individual characters. If the message is complete, then the execute instructions function is runs, and this function processes the message and uses the information to control the actuators. For example, we get a message, run this pump, then in this execute instruction function, the pump then is run. So this is basically, these are the both functions needed for the computer message to be received and processed. On the other side, we want to send information or data to the computer. And for this, we have the send data function. If it is time to report new measurement values, which depends on the sampling rate, the send data function is called. And this function sends the measured values to the computer, basically. And this is the general setup of the code on the Arduino Nano microcontrollers. It differs a little bit depending on the module, but you're gonna find these functions on every of them. So now we have the basic building blocks. Let's look at the final graphical user interface we can build with that. You can see it here. This is the graphical user interface, and here you have the process flow diagram. In this process flow diagram, you have some widgets, which are some buttons and some entry fields you can use to interact. For example, here we have the feed button, and after this, upstream of this is the feed pump, and here we can insert the volume flow rate of the feed pump and send it to the Arduino Nano microcontroller. Afterwards, the pressure is gonna increase, and we can read the actual pressure here, which are 185 centimeters of hydrogen as a pressure scale, because that's the way I calibrated the pressure sensors. So then you have here the fractionating column with the evaporator at the bottom, and here the overflow with the bottom product, and at the head of the column you have the condenser, where over and overflow the top product is removed or withdrawn, and you have the reflux pumps which pump a fraction of this condensate back into the column. The condenser is cooled using cooling liquid, and this cooling liquid, as you can see, is introduced countercurrent wise to increase the temperature difference and therefore the efficiency of heat transfer. And the cooling liquid comes from this recooler unit you see here at the left. In this recooler unit you have this container, you have the coolant pump, and you have the 360 millimeter radiator with the fans. You can individually start and see their speed. So in this process flow diagram, we can basically control the fans, we can control the pumps. What we don't can control are the temperature, or is the heating element. For their control, we have this frame at the top of the graphical user interface, the temperature control frame. Here we can choose which temperature we want to control and set it to the desired value, which works for the temperature 1 and 2. For the temperature 3, it doesn't really work that good. We're gonna see it later. Here at the right of the graphical user interface, you can see the temperature plotted over time and also the pressures of the pumps plotted over time. So that basically is the software, and we now have all the components. Let's look at the control scheme necessary to achieve steady state operation of this fractionating column. So here we have again the flow chart, the process flow diagram of the fractionating column. And to achieve the steady state, we shouldn't accumulate gas or liquid inside of the column, because if we accumulate something, gas or liquid, inside a column during operation, it is not a steady state. The liquid accumulation we can prevent by controlling the liquid levels. And we use this simply using overflows, shown here or marked here in green. The gas accumulation we can see by changing pressure inside the column. And we control that by changing the surface area available for condensation inside the condenser. This one is a little bit more complicated. Let's have a look at it. If the pressure inside of the column increases, then the liquid level inside the condenser is pressed down. Yeah, we have the liquid level is chosen in such a way that we have liquid inside a condenser. And if the gas pressure is high enough, it pushes the liquid down, and therefore new heat transfer area is free for condensation of vapors. And at this increased heat transfer area, condensates more vapors, and therefore the amount of gases is reduced inside the column and also the pressure. That's the idea behind this pressure control. So next we have the temperature, or next we have, or using these both methods, we have a steady state. At least we have no accumulation of gas or liquid inside the column, but we also want to reach or guarantee a certain product quality or a certain concentration in our products. And this is difficult to control using classical chemical analysis tools because they are too slow most of the time for control loops. Therefore, often the temperatures inside of the column are used as an indicator for the composition of the products, and therefore the temperatures inside of the column are used and controlled using the heater input, for example, and therefore guarantee a constant product quality. So this control scheme is called a mass balance indirect scheme. There are different control schemes. You can find them in literature, but this is the simplest one that I found for our application and what I chose at this point. The difficult part at this point is the temperature control inside a column. Therefore, we look at this temperature column, temperature control in a little bit more detail. Why it is difficult? Because the temperatures 2 and 3 inside a column, they change much slower than the temperature of the heating element. Yeah, the heating element temperature, the temperature probe is connected directly to the heating element, and if I put power into it, the temperature almost immediately increases. But for the temperatures 2 and 3 to increase, we have to heat up different parts of the column. We have to generate steam which rises inside the column, which also heats up some refluxing liquid and something like that. So it needs more time. And now the problem is as following. If we want to have a certain temperature inside a column and don't reach this temperature as fast as we think we need to reach it, then we increase the amount of power we put into the heating element, but it needs time for this power to result in the temperature change. And if we don't wait for this time, we increase the power even further and further and further, and therefore have the risk of overshooting or even damaging or killing our heating element. In order to solve this problem, we could use something called a cascaded controller. In this cascaded controller, we have an outer loop or primary loop, shown in green in this scheme. And this outer loop, it controls the column temperatures 2 or 3, and it is slow. Yeah, the controller reacts very slowly, therefore also that's one reason why I have an integral controller only here. And the temperature of the heating element, which we want to control closely in order not to overheat the heating element or kill it, is controlled by this inner control loop or the secondary control loop, and this is quite faster. And the outer control loop basically provides the set point for the temperature of the heating element in the inner control loop. And that's the way we couple both of those control loops and are able to more or less control the temperature inside a column without having this risk of overshooting and heater damage. I want to show you that this works somehow with this test. Here you can see the schematic again to see where the temperatures are located, the temperature 1, 2, and 3. And here you have the diagram with the temperatures over time. We've chosen temperature 2 to be controlled in this case. And as you can see, the outer control loop, it increases the set point for the inner control loop for the temperature T1 also. And the temperature of the heating element is relatively close to the set point in most of the time. So this control loop is quite fast and good. But as you can see here, the temperature of the at a point 2 lags behind the set point temperature for a longer time. And the reason for that is that we need to heat up a lot of liquid and generate the steam to reach this temperature probe at first. So we have a lag element inside there. But with the help of this outer and inner control loop connection, we are able to more or less control or more or less reach our final temperature we want to reach or temperatures we want to reach. You can see in this experiment that we have a high fluctuation in the temperature reading of temperature 2. The reason is as soon as evaporation, as boiling starts, there are bursts of vapor reaching the temperature probe 2. Here you have bubbles of vapor rising inside the evaporator, and if they reach the temperature probe, if a big bubble reaches it, then the temperature increases and so on, and therefore we have high fluctuations in here. And that's also one reason why I choose only an integral controller for the outer control loop, because this is able to average over these fluctuations and is able to hold the temperature more or less in average on the or in the model value, in the median value on the desired level. As you can see with this control scheme, we are able to control column. Now we have everything together to run it. So basically run the column. And you can see the column under operation in this video. Here we have the graphical user interface with the actual values of the sensors. The feed is pumped inside of the column and flows down into the evaporator section. There the bottom product is also withdrawn. The vapors generated inside of the evaporator rise inside the fractionator column. Here you have a quick look at the packing material, and they are condensed in the condenser. The cooling liquid for the condenser comes here from the wick cooler. You can see the fans turning, and the reflux pump, you can see it working, pumps the reflux flow inside the column at the top. Here you can see the overflow for the top column product, and you can see the product drops inside the beaker. This is the refractometer, which is then used to analyze the top and bottom product. Okay. Here you can see the temperature graphs in this experiment. In this experiment, I tested what are the maximum temperatures I can achieve with this setup, and I was able to achieve wall temperatures of the evaporator of around 180 degrees centigrade. I don't want to increase it even further because of the decomposition of propylene glycol, which starts at higher temperatures and which results in residue inside the evaporator. You can also see that at the higher temperatures, the temperature 2 and 3, they don't change much with increasing heater wall temperature, because as soon as boiling is achieved and vapors are rising, the boiling point and the boiling temperature stays the same inside the evaporator, and therefore the liquid temperature. Showing that we have some kind of steady state, by the way. Okay, now let's look at the products of this fractionating column. Here you can see the feed used in this experiment, which were 702 grams of a water 1,2-propane diol mixture, which is propylene glycol, and we have 63 mole persons of water inside this mixture. You can analyze this using the refractometer. This is a refractometer basically for automotive applications, and in this it is used to propylene glycol is used to decrease the melting point or the freezing point of the cooling water. Therefore, you have the cooling point temperature as a scale, but with the help of calibration of this refractometer, I know which freezing point corresponds to which concentration. In order to measure such high concentrations of propylene glycol, I diluted the sample 1-to-1 mass by mass with water. So putting this inside the column, out of it comes 30 grams of top product, and as you can see from the refractometer measurement, we are close to the waterline, and if you round a little bit, then we get around 100 mole persons of water inside the top product. These are not true 100%, but 99 point whatever, and but we obviously removed a lot of propylene glycol from the top product. And then we have the bottom product, which are 659 grams. And in this bottom product, the concentration of water decreased. We have this water now in the top product to 58 mole persons. You can also see this in a decrease in the freezing point temperature. Yeah, the line moves slightly up compared to the feedstock. You can also see that if you sum up both of these values, we lost some of the liquid inside the apparatus or through leakages. Yeah, that happens at this point. So basically, this shows that the apparatus works. Yeah, that the fractionating distillation column truly can operate in steady state, automatic, controlled conditions and continuously, and therefore we more or less achieved our goal to build such a fractionating column. With this, we are at the end of this video. I hope you have enjoyed it, and if you looked it until now, huge thanks for all your patience and for sticking to it until the end. You can find all the codes for running this apparatus and also the slides I shown here on my GitHub page if you want to look at it in more detail. And yeah, thank you for watching. Until the next time. Bye.